Okay, here are some notes that come out of the textbook in Chapter 6. In Chapter 6, we're going to be dealing with systems that have masses, liquids, gases that will flow in and out of the system. We haven't had that before, at least not in Chapter 5. And so we're going to do energy and mass on these things. This diagram shows the differences in the equations. On the left-hand side, this would be a non-flowing fluid, which is what we've been using for most of this. There's internal energy, you have kinetic energy, you have potential energy, and all of those are the energies in the fluid. If the fluid is flowing, you have this what's called flow energy. This is the energy that's required to push the fluid into a system, or it's the energy you get out when the flow comes out. So anyway, you've got that's called flow. You still have the internal. So if it's hot, for example, you've got a lot of internal. You can still have kinetic and you can still have potential. So it's this flow energy that's new in this particular chapter. There's a definition where this happens so frequently, the flow energy plus the internal, that they define enthalpy, which they always write it as an H, and it's equal to the U plus the PV. So if you combine these two terms together, you'll get the H, and they'll tabulate the H. So the energy then would be H, kinetic, potential, and from the input and the output. So that's the one there. Okay, so energy transport by mass. So this is the flow work basically. So here's the energy that that the mass brings in. This is for the total energy. So this would be written for all of the mass that occurs. Sometimes we're going to write it as a rate, like a watt would be the rate that you get joules. So a watt is joules per second. So that's how fast. And really, basically, the only difference is that you have, instead of total mass up here, you have the rate at which mass moves down here. So it's essentially the same, but you have to make up your mind which one you're going to do, either rate or total energy. Okay, there's something called a steady flow. What a steady flow system is it's a system that doesn't change, and so theoretically the thing could run forever. And we're going to write mass equations and energy equations for these things. So, for example, the mass, whatever flows in, the rate at which it flows in is equal to the rate it flows out, because nothing is accumulating inside. And then there's these relationships between, I'm sure you've seen these before, between mass and the density, area, and velocities. So these are mass terms, and the same thing up here. Okay, for a steady flow, the change in energy is equal to zero. Nothing's changing inside. So you end up with an energy balance. We'll do some homework problems with this. And you can write it as a rate. So this would be the energy form as a rate. I think it's easier to just, rather than memorizing an equation, I think it's easier to just think about what the energies are and then add them in there when you have them. Okay, so here is the energy written as a rate. The rate of work is called power, and that would be measured in watts. Okay, so here are some steady flow devices. Here's a nozzle. Basically, it's just a piece of metal or a tube of any kind. It's essentially a pipe that has a changing diameter. So it's like a cone shape. It doesn't have to be straight lines on the side. I mean, they could be curved here or whatever, but it's basically just a pipe that's changing its diameter. So if the flow is going from big to small, they call it a nozzle. If the flow goes from small to big, then they call it a diffuser. Okay, then we have turbines and compressors. They're written with boxes like this. Typically what will happen is if it's a compressor, the inlet is larger, so this would be a compressor. The fluid would go in, and these blades, you can see a picture of them over here, Very intricate, but the blades then smash the fluid together, make it more and more dense. And then when it comes out over here, it comes out at different pressure and temperature. If it's a compressor, you have to put energy into it to get the energy. You want to transfer this energy here into the air or steam or whatever you're compressing. If it's well insulated, they call that adiabatic, and there's no heat across this. So this would be a compressor. For a turbine would expand. So you would put the flow in the small end, and then it would push against these blades and expand as it gets bigger and bigger, and then the mass would come out the large end. Then if you're expanding it, you're getting energy out, and it will drive the shaft for you. So that's the difference between a compressor and a turbine. Okay, a throttling valve, basically it's a flow limiter. And so what happens is you can have you're basically putting a restriction in here. So you can turn this knob down and close the valve a little bit. And what it does is it restricts the flow across here, and you'll get a pressure drop across the valve. So that's typically the way you would control the flow. You do this in your garden hose and whatnot. There's different ways you could do that. This one has a valve. People, I think, are used to that. You can have a porous ring someplace that's got the little holes in it. It's hard for the fluid to get through. Or you can make a real skinny tube. So there's different ways you can throttle that back. So these are used a lot if you have a massive pump on one side. It's producing too much pressure for whatever you want over here. Too much flow, too much pressure. You can throttle it back, and you basically you're throwing away energy is what you're doing. So typically on these, there's no heat transfer. There's probably a little bit, but the area is so small, a lot of people just ignore that. So these are the equations that typically occur in that. And you get this by doing conservation of energy and mass. Okay, mixing chamber. You do this in your shower all the time. You take some hot water, some cold water, and you adjust the amount that you allow flow in so that you get a certain temperature on the outside. In an industrial sort of thing, you can do the same thing. You can just put in two different flows, and they have a corrugated area to cause these fluids, gases, liquids, whatever they are, to mix, and then it comes out as a mixed on the other side. Typically, they try to insulate these things. There's not much area, so you would say that there's very little heat transfer. There could be some, but the typical assumption is that there's no heat transfer, and there's no work. There's no place for any energy to come out for you. Okay, and then also your kinetic energies and all are usually small. Okay, so here's a heat exchanger. It's designed to exchange heat. So a hot fluid is trying to give energy to a cooler fluid. So you would have, say, a hot fluid coming in through the pink, and a colder fluid that would go through the blue, and then the energy would transfer from the hot to the cold. And so typically, you try to prevent any heat coming out of the system. You want all of your energy to transfer from the hot to the cold. So the Q is not zero when if you're treating it one fluid at a time. But there's no work coming out of this. There's no shaft or anything that you're getting any work. And that's it. So let's do some problems.